All right, let's talk about something we do every single second of our lives. Move. Have you ever really thought about what's going on behind the scenes? Every step, every leap, it's all run by an invisible set of rules. Today, we're going to pull back the curtain and decode the fundamental physics of human movement. We're talking about the principles that turn simple pushes and pulls into, well, the incredible, complex motion of the human body. And look, this stuff matters to all of us. Whether you're an athlete trying to get that extra edge, a therapist guiding a patient back to health, or honestly, even if you're just curious about how your own body works, you are constantly playing by these rules. So let's do it. Let's make those invisible rules visible. Okay, so here's the plan. We're going to start with the basics, the language of forces, then we'll jump into the famous laws of motion. After that, we'll see how forces work together, and finally, we'll bring it all home by looking at action, reaction, and some real-world forces you deal with every day. All right, first things first, we've got to learn to speak the language. So, let's start with the main character of our story today, force. What is it really? Well, at its absolute core, a force is just a push or a pull on the body. That's it. We're going to focus mostly on external forces, things coming from outside of you. And the cool thing is, physics gives us this incredible, simple little equation to wrap our heads around it. F equals m times a. Force equals mass times acceleration. Remember that one, okay? It's kind of the key to everything we're talking about today. Okay, this leads us to a really, really important idea. The difference between a scalar and a vector. So think about mass. It's a scalar. It only has a magnitude, a size. It's like saying it's 20 degrees Celsius outside. You don't say it's 20 degrees Celsius up, right? But force is a vector. It has both magnitude and direction. You can't just say you pushed with a lot of force. You have to say which way you pushed. That direction? It's absolutely everything when we talk about movement. And speaking of forces, there's one that you can never, ever escape. What's the most constant, persistent external force we all deal with 24/7? Yep, it's gravity. It's that relentless pull between the mass of the Earth and the mass of your body. It's always on, always pulling you down, and our bodies are in this constant, lifelong negotiation with it. Okay, so we've got the language down. Now, let's open up the rulebook. We're diving into Sir Isaac Newton's legendary laws of motion. So before we jump right into the laws, we need to get two key ideas straight: statics and dynamics. Think of it like this. If all the forces acting on you are perfectly balanced, they cancel each other out. You're either staying still or moving at a steady speed. That's statics. But the second those forces get unbalanced, you accelerate. That's dynamics. It's literally the difference between holding a yoga pose and exploding off the starting block. All right, law number one, the law of inertia. I like to call this the law of stubbornness. Seriously, it just means that an object is perfectly happy doing whatever it's already doing. If it's at rest, it wants to stay at rest. If it's moving, it wants to keep moving in a straight line at the same speed. It'll just keep on doing its thing until some outside force comes along and messes it all up. And that stubbornness has a name: inertia. It's just an object's resistance to any change in its motion. And here's the kicker. The more mass something has, the more inertia it has. The wheelchair example is perfect. Think about it. It takes way more effort to get a heavier person in a wheelchair moving from a standstill than a lighter person, right? That extra effort you're putting in, that's you fighting against more inertia. And look who's back. Our old friend, F equals ma. Newton's second law basically puts numbers to the first law. It tells you exactly how much force you need to overcome that inertia we just talked about and make something accelerate. The relationship is super straightforward. You push harder, you get more acceleration. But if the object has more mass, you're going to get less acceleration for that same push. Makes sense, right? So if we're going to talk about force, we need a way to measure it, right? Well, the standard unit is called the Newton, named after the man himself. And its definition comes straight from that F equals ma equation. 1 Newton is the amount of force you need to take a 1 kilogram mass, so think of like a big pineapple, and get it to accelerate at 1 meter per second squared. It's the perfect unit because it connects force, mass, and acceleration all in one. Okay, so in the real world, it's pretty rare for just one single force to be acting on something. It's usually a whole team of them. So let's take a look at how these forces work together. The simplest way forces can interact is in what we call a linear force system. And the best way to picture this is just a classic game of tug-of-war. You've got two or more forces acting on the same object all along the same line. They're either helping each other out or working directly against each other. Simple as that. So, how do we figure out who wins the tug of war? We find what's called the resultant force. It's way easier than it sounds. It's just 3 steps. First, you just identify all the forces in the game. Second, you pick a direction to be positive. Let's say pulling to the right is positive. That means any force pulling to the left is negative. And third, you just do the math. Add them all up. The final number tells you not only who won, but by how much and in which direction. Of course, things are usually a bit more complicated than a straight tug of war, especially in the human body. We're constantly using what are called concurrent force systems. Now, imagine 2 people trying to pull a heavy box, but they're pulling from different angles. Their forces meet at a single point on the box. That's a concurrent system, and this is happening inside you all the time. Think about your deltoid muscle in your shoulder. Different parts of that single muscle pull on your arm bone from slightly different angles to lift your arm. It's incredible teamwork. All right, we're heading into our final section. We're going to tackle Newton's third and final law, and then we'll really get into the nitty-gritty of some specific real-world forces you'll see in biomechanics. Okay, Newton's third law. You've definitely heard this one. For every action, there's an equal and opposite reaction. But have you ever really stopped to think about what it means? It means forces never ever show up alone. They always come in pairs. When you push on a wall, the wall is pushing back on you with the exact same amount of force. It's not a suggestion, it's a rule that governs every single physical interaction in the universe. Here's a great little mind bender that proves this point. When you step on a bathroom scale, what is it actually measuring? Now, 99% of people would say, my weight, which is the force of gravity pulling down on you. But that's not quite right. The scale can't feel gravity. The scale can only feel the force that your feet are pushing down on it. And because of Newton's third law, that downward push from you is perfectly equal and opposite to the upward force the scale is pushing on you to keep you from falling through the floor. It's that reaction force it's measuring. A subtle difference, maybe, but it's a perfect illustration of this law. Okay, so how do we apply all this inside the human body? Let's wrap things up by looking at 3 really key forces that are critical in biomechanics. We're talking tensile forces, shear forces, and friction. First up, tensile force. This is just a pulling force. Think about a rope in a tug of war, that's tension. In your body, it's what happens when your bicep muscle contracts and pulls on its tendon to bend your elbow. And a special kind of tensile force you'll see is joint distraction, where you're essentially pulling on a joint to create space. Next, we have shear forces. These happen when forces act parallel to a surface, but in opposite directions, kind of like sliding a deck of cards. This happens between your vertebrae all the time. And finally, you've got friction. That's the force that resists all that sliding. Luckily for us, our joints are amazing at minimizing friction thanks to smooth cartilage and synovial fluid. So there you have it. We've gone all the way from a simple push or pull to the fundamental laws that govern every single move we make. And what's so amazing is that the principles themselves are actually pretty simple, right? But how they play out inside the human body, well, that's almost infinitely complex. So the real question I want to leave you with is this. Now that these invisible rules are a little more visible to you, how are you going to apply them? How will you use them to better understand, analyze, and ultimately improve human movement? Something to think about. Thanks for joining me on this one.